Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Here we see our textured model, which looks perfect if it was in a game from 1995. However, for a modern game, it's missing a few visual enhancements. One improvement that we are going to focus on in this episode is adding finer details to the surface of the model as if it was a high-resolution geometry. This can be achieved by using a technique that goes by the name of normal mapping. Although applying a normal map is rather straightforward and can be done in less than 10 lines of shader code, it's important to understand the mathematics behind normal map construction and application for anyone who is aspiring to become a better graphics programmer. As we saw in the earlier videos about lighting calculations, we need a normal vector in order to determine how much light is reflected by the surface. On a smooth mesh without hard edges, normal vectors of each triangle are averaged over their shared vertices. This vector is then sent to the vertex shader as part of the vertex data. In order to calculate lighting per pixel, we use the interpolated normal vector in the pixel shader. Although this is sufficient for smooth meshes, it's not enough for simulating the majority of common surface types we see in the real world. Most objects have a lot more surface variation, which is often captured in a high-resolution 3D model using millions of polygons. However, it's mostly impractical to use the high-res models directly as game assets. Instead, a low-resolution model is used with fewer polygons. If we had a way to know what the normal vector in the high-res model would be at a certain position, we could still use that vector for lighting. Fortunately, there is a method for recording normals at each pixel in each triangle. If the 3D mesh has a UV set for texturing, then we could use a texture that contains vectors instead of colors, and we could sample the normal vectors from the texture, which is called a normal map. As I mentioned, the RGB channels of the texture contain the X, Y, and Z components of a vector in 3D space. Furthermore, since this is a unit vector, we only have to put the X and Y components in the texture. The Z component can be calculated in the shader. In general, normal maps are calculated in the software that was used to create the 3D model, or some texturing application like Adobe Substance Painter. So now we have these vectors, but what coordinate system are they related to? Obviously, they can't be in world space, since that would make them invalid as soon as the object is rotated in any direction. Also, we couldn't use object space, because deforming the object by scaling it or during an animation would invalidate the vectors. One coordinate frame that's invariant, however, is the one used for the texture coordinates, or the UVs of the model. So we can use that to construct a coordinate system. Using the UV coordinates, we can construct two perpendicular vectors on the plane of a triangle. Since these are parallel to the triangle, they are called the tangent and bitangent vectors. We can use tangent and bitangent vectors together with the interpolated normal vector to form a tangent frame. Don't worry, I'll try my best to explain. Let's consider this triangle with three vertices with position P0, P1, and P2. Each vertex has its own UV coordinate in the texture space. We can calculate a vector that points from one vertex to another by simply subtracting one vertex's position from another one. Now we want to find two axes on the plane of this triangle, such that subtracting the UV coordinates of the same two vertices would yield the exact same vector in this coordinate system. This is kind of the central equation in this entire explanation, so please take a moment to understand it. T and B are 3D vectors in object space that form a 2D coordinate system on the surface of the triangle, such that the edge vector of the triangle is the same in this coordinate system as it is in object space. We can try to find T and B by taking the edge vectors and write two equations with two unknowns, which can be solved using a bit of linear algebra. First, let's name each component so that we can write the equations down using a more compact notation. Next, we write them in a matrix form. Let's call them A, B, and C, where we know the values of all components in matrices A and C. Matrix B can therefore be calculated by dividing matrix A by matrix C. Of course, there is no such thing as a divide operation for matrices. However, we can achieve the same result by multiplying A with the inverse of C. Matrix inversion is a topic of linear algebra and I'll not explain it here, but it can be calculated easily for 2x2 matrices. We can even use an online calculator to do it like so. Now we can plug this in our matrix equation here, which gives us the solution. As you can see, the right-hand side of the equation can be calculated since all values are known. Now that we have t and b vectors, we can form a tangent space together with the vertex normal. However, before using that as is, we need to realize that both t and b are on the triangle plane, whereas the normal vector is averaged over multiple triangles. Therefore, the axes of the tangent frame aren't orthogonal to each other. We can, however, nudge them a little in order to make them orthogonal. Suppose we have a unit vector A and another vector V. We can compute the projection of vector V onto vector A. This is the component of V that's parallel to A. We can calculate the rejection of V from A simply by subtracting the parallel part from V. This is the component of V that's perpendicular to A. This procedure is known as the Gram-Schmidt orthogonalization. We can use this to calculate the perpendicular part of T with respect to normal vector n. Now that we have the two unit vectors that are orthogonal to each other, we can calculate another vector that's perpendicular to both T and n by taking the cross product of the two vectors. This is the B vector, which can be calculated in the shader. However, we need to remember whether the coordinate system is right-handed or left-handed. For this, we need to look at the original value of vector B that we got from our matrix calculation and see in which direction it's pointing. Then we can define a value, sigma, that's +1 if the cross product of T and B points in the same direction as the normal vector, otherwise it's -1. In the shader, we can use the perpendicular unit T vector, the normal map and the value of sigma to calculate B. The three vectors T, B, and N form an orthonormal coordinate system where T stands for tangent vector and B stands for bitangent. As the naming suggests, both vectors are parallel or tangent to the polygon surface at the vertex for which we calculated the vectors. When a vertex is shared by multiple triangles, the vectors are averaged in the same way we averaged normal vectors. The interpolated tangent space is used as the basis for the normal vectors in the normal map. Let's write a function that calculates the tangent vectors. This function will be called if the import settings require the importer to calculate tangent vectors, or the FBX file didn't contain any tangent information, in which case the tangent array would be empty. Of course, we can only calculate the tangents if the model has a UV set. First, we clear the tangent collection that might have been imported, since we are going to calculate our own. We are going to calculate the tangent per triangle vertex. So before averaging the tangents, we have as many tangent vectors as there are indices for the mesh vertices. That's why we need an array with enough elements to hold as many tangent vectors. Also, I'm using XM vector type from DirectX Math library since we are going to add the tangents together, as we'll see in a minute. Additionally, we need a similar array for bitangents and one for vertex positions. The positions array is just a cache so that we don't have to load each position vector every time we need it for calculations. Now we can look at each triangle within the mesh and calculate the tangent and bitangent vectors for each one of its vertices. This is the implementation of the matrix solution that I explained earlier. First, we get a reference to each of the triangle's vertex positions and UV coordinates. Using these, we can calculate the differences in UV coordinates as well as the position vectors from the second and the third vertices to the first vertex. The determinant of the UV matrix is calculated next. However, it can happen that the UV coordinates of two vertices coincide, and in that case, the determinant will be 0, which will cause a divide by 0 error, resulting in invalid tangent values. In that case, we give the determinant some small value just to prevent invalid calculation results. Now we can compute the t and b vectors. Finally, we add the resulting vectors to the tangent and bitangent vectors of all three vertices. The last step is to orthonormalize the vectors and determine the handedness of the tangent frame. As I explained earlier, we can use the rejection of t from the vertex normal to get the component of t that's perpendicular to n. Finally, we determine the handedness of the tangent frame and put it in the w component of the tangent vector. That's all we need for calculating tangent vectors. When we pack the vertices to be saved in a mesh asset file, we are not going to use a full floating point value just to save the handedness, which would be wasteful. Instead, we'll use a single bit. However, the way it's done currently is incorrect and I need to fix it before we continue. I'm doing this weird thing by adding these two booleans, but we actually need 2 bits. One for sign of the z component of the tangent vector and another one for the handedness. I think I need to add a comment here. Let me see if this enum is actually a duplicate. I guess not. Well, anyway, here we see that we are using the first bit for the handedness and the sign combined, which is indeed incorrect. The second bit is used for the sign of vertex normal's z component. To correct this, we have to use the first two bits for the tangent vector and the third bit for the normal vector. That means that when we pack vertices, we have to shift the bit for normal sign one more to the left to make room for the tangent bits. And then we can put the bits for tangent handedness and z component sign in the first and second bits respectively. And that's all we need to change here. Since the normal bit position is now changed, we need to update the C# mesh renderer so it reads the correct bit when we view a model in the geometry editor. This should do the trick. Of course, we also need to update our shader code, which again I'll edit in Visual Studio 2019. First, we need to add an extra component for the handedness to the world tangent vector that we calculate in the vertex shader. Then we update the normal sign bit position in here as well. We can write this in an even compactor form. We do the same thing for vertices with UV coordinates, but this time we also need to read the tangent information. So the tangent z component sign is in the second bit and the handedness is in the first bit position. By subtracting 1 from each of these, we get either +1 if the bit is set or -1 if the bit is not set. Then we can unpack the tangent vector in the same way as we did for the normal vector. It's possible that the two vectors are not orthogonal anymore because of the loss of precision during packing and unpacking. We can use the Gram-Schmidt orthogonalization here again in order to restore their perpendicularity. When transforming vectors, we only need the rotation and scale part of the transform matrix, which are both in the first 3 rows and columns of the 4x4 matrix. After transforming the tangent vector and normalizing the result, we put the handedness in the W component of the tangent vector. Oops, this should be tangent. And here the result is a 3D vector, so we don't need to explicitly get the x, y, z components. I'm missing a parenthesis here. And we are ready to use the tangent space for normal mapping. In the next video, I'm going to explain how we can use the values in a normal map texture in order to calculate per pixel normal vectors. And of course, we are also going to implement normal mapping in our pixel shader. Thank you as always for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering.